Hey, welcome back to Math with Patrick. Today is March 9th, and we have problem number 68 from this Daily Epsilon calendar. All right, the answer is 9. That's today's date, and we need to show why plugging in a 9 right here works. Now, I could do it like knowing the answer is 9. I could plug in a 9 right here, 9 minus 2, do 14 divided by 9 minus 2, but I want to assume that I don't know what the answer is and come across this 9 on my own. So I have an equation and let's just solve it kind of a traditional algebra way, where I'm just going to use some opposite operation steps to unfold this equation in a way and solve for x. So the first thing I notice is that my x is tucked away in two different denominators. There is this denominator here, and then there's another denominator in my denominator. I have fractions within fractions. And I don't know about you, but I much rather work with whole numbers than fractions. One way to get around this is to multiply on both sides of your equation. So if, for example, if we had 1 over x equals 5, and my x is in the denominator here, it's a little bit weird, you could multiply both sides by x. And we get 1 equals 5x. And here, at least for me, it's a little bit better. I'm not dealing with fractions. I could then see that I could divide both sides by 5, and I get my answer. There are other ways to solve kind of these easier equations that I just showed on the right. However, hopefully now you can believe me that I could multiply by the denominator and further simplify my equation. So I know that 12 is going to be equal to 3 times the whole denominator. And it's really important that I'm using parentheses here because that 3 is going to distribute to both of these terms. So I'll say 12 is equal to 18. That's a 3 times a 6. Minus 42. That's 3 times a 14 over x minus 2. Same issue. I have more denominators and I don't want fractions. They're harder to work with. So the algebra step that I want to take now is multiplying. I want to multiply all three of my terms by x minus 2. Mind you, I have to do all three because here, for example, I think we can both agree that 1 plus 1 is 2. But if I decide to multiply up only 2 terms and not the third, then I'm going to get something that doesn't make any sense anymore. 1 plus 3 is not 6. So if you are doing this multiply step, you need to make sure that you do it to everything. So I'm going to multiply everything by x minus 2. So I'll get 12 times x minus 2 equal. Actually, you know what? What am I doing? I want to simplify a little bit first. Let me combine like terms. I'll subtract 18 and subtract 18. So I get negative 6 equals negative 42 over x minus 2. And then here, if you have a negative something equals another negative something, the negative signs can go away. You know what? I'm really glad I did that because I don't need to do that whole times x over 2 stuff again. There's actually maybe a neat algebra trick here. If you have some kind of fraction equaling a whole number, you can swap the positions of these two. So c over 5 is going to be the same thing as x. And to just kind of prove that, you could take it step by step. You could multiply both sides by the x, kind of like I did earlier with that 1/5. These cancel out. And then now you could divide by 5 on both sides. And what do you know? Here's that conclusion that I came to already. So if you have a scenario where you have a whole number equals a fraction, you can just kind of quickly do 2 steps at once and swap this denominator for this number on the left side. And I can evaluate 42 over 6. That's just the number 7. And from here, adding 2 to both sides, I can now see x is 9. Great. That's today's date. So we're all done. Just kind of working through it algebraically totally works. If you want to stick around, I do have a second way to potentially solve this. And I don't know, maybe it's worth it. So another way to think about this is with opposite operations, but this time you can kind of list out what is happening to x? So here's a second way to solve it. What's happening to x? So we start at x right here. The first thing that happens is I subtract 2. Okay. The next thing that happens to that whole chunk is I do 14 divided by it, not divided by 14. That would look like this. I'm doing the other one. I'm doing 14 divided by it, like that. So I'll say 14 divided by it. Then the next thing that's happening, I want to take it step by step. I'm negating it next. That's this minus sign. There's a negation. Then I'm adding 6 because this is a positive 6. Finally, I'm doing 12 divided by whatever it is. So 12 divided by it. And then finally, this is supposed to equal the number 3. And it would take a lot of work, a lot of legwork to do guess and check here. You plug in a 2, subtract the 2, do 14 divided by 0. Oh dear, I just broke math. Instead of working top down, you can work these things bottom up as long as you remember some inverse operations. So let's start at the number 3. And we need to do the opposite of doing 12 divided by it. Now, here it might be kind of easy for me to say, oh, the opposite of 6, adding 6 is subtracting 6. But it's a little bit harder to think about what's the opposite operation for this. Now, let me see if I can convince you. So let's say I have some function f of x, and that's going to be 1 over x. If I input, say, a 2, I'll get 1/2. So what happens if I apply this function a second time? I want to do f of 2. Well, earlier I said that this is a 1/2, and then now just using the function rule, f of 1/2 will be 1 over half, which is 2. So applying a 1 over x function 2 times to some number, it'll return you back to the number that you started out with. Or in other words, to undo this f of x function, I can just do the exact function. Now, it doesn't really matter that that was a 1. This could also be true. It is also true when we have any constant number there on the top. So when I'm trying to do the opposite of, I think it was, 12 over it, the opposite of that operation is just itself. So doing the opposite of 12 divided by it will be the same thing. I'll do 12 divided by it, which is, right now it's a 3. So 12 divided by 3 is 4. Okay. The next thing I should do is the opposite of plus 6, which is minus 6. So I'll get a negative 2. You know what? Let me write out all my steps. I'll go 4 minus 6 is negative 2. There we go. Then negation. So the opposite of negating is just negating again. So if I have a 5 and I negate it, cool, it's negative 5. And if I negate it again, I'll get back to where I started. So kind of like doing that division step, this is like a self-inverse step. I can just negate it again. So the negation of negative 2 now brings me to the number 2. 14 divided by it. So I need to do 14 divided by 2, which is 7. And then finally, to undo a minus 2, I'm going to do a plus 2. 7 plus 2 is 9. And that's the same 9 that I had before. So the steps that I just took here are algebra steps, just like I did before. But it's a different way to think about it. If you can try to figure out the steps that lead from x to your answer, you can work backwards and do these inverse operations in opposite order and still get to the same answer. So there's 2 different ways to make sure that the answer today is indeed 9. Now, if you're studying algebra, I would recommend the left side because that strategy is applicable for many things. But if you want to challenge yourself to think about inverse operations and inverse functions in a new way, then I don't know, try out the right side. That'll be up for you to decide. So thanks for coming along. I'm happy to show you 2 different ways to solve this problem, and I'll see you tomorrow. All right, bye-bye.